welcome to today's webinar, Building Smart Applications with Amazon Machine Learning. Our presenter today is Alex Ingerman. Alex leads the product management team for Amazon Machine Learning. He joined Amazon in 2012 after working on products including web-scale search, content recommendation systems, immersive data exploration environments, and enterprise email and content servers. Alex holds a Bachelor of Science degree in Computer Science and Master of Science degree in Medical Engineering. Today with us, we also have Nicole Correa, Senior Technical Program Manager for Amazon Machine Learning Platform, Victoria, Senior Product Marketing Manager at AWS, Charles, General Manager of Amazon Machine Learning. They will engage with you and answer your questions throughout today's presentation. Alex, welcome, and I'll pass the floor to you.
Thank you, Bowen. Hello. Thank you very much for joining us today. As Bowen said, my name is Alex, and today I want to talk to you about how real-world smart applications can be built with Amazon Machine Learning and a few other AWS services. So, I find that the best way to learn to do anything is to follow a real-world example. In this session I would like to present to you today, I would like to show you how to build an application in AWS Cloud that can be used to accomplish something that's very important to many businesses, and that is listening to social media. What I'd like to show you specifically is why it is important to listen to social media streams like Twitter, Facebook, or LinkedIn to find customers who may be using these channels to reach out to you. I won't dwell too much on the social media industry itself. Instead, I want to jump right to talking about how you can use AWS to find only the important conversations within the social media stream and then act on them. I'll be talking a lot about Twitter as a social media channel during this presentation. And maybe this example is not as interesting to some of you in the room. Maybe it's not a channel that your customers use to talk to you. But there is nothing specific to Twitter in the machine learning process that I'll walk you through. It will also work with emails or reviews or folks filling out contact forms on your website. So stick around. To start off, I want to show you our goal for the session, and that is to build a smart application, again, for listening to social media streams. And we'll use several AWS services together to accomplish this. We'll, of course, use Amazon Machine Learning to create predictive models that can inspect a social media event coming in and decide whether it's actionable or not. We'll use Amazon Kinesis to ingest data into AWS Cloud. We will use AWS Lambda for executing code without provisioning or deploying services. Then we'll use Amazon's Simple Notification Service, or SNS, to enable robust push notifications. And finally, we'll use Amazon Mechanical Turk for annotating our data prior to machine learning. If you don't have experience with some of these services, don't worry about it. I'll describe what each one does as we go along. And I'll be showing you a lot of code as we go along. The complete code and a sample dataset for this application is available from the AWS GitHub account, and you can see on the slide a bit.ly link to access that account, and I'll show you that link again at the end of the presentation. And just as a reminder, all slides will be available after the session concludes. So let's start with motivation. Why should we listen to social media? Here is one tweet that I grabbed from Twitter. It's addressed at AWS Cloud, which is the official handle of Amazon Web Services. And here we have an example of a customer who is reporting a problem. Do we want to do something about this tweet? Is it important? I say, absolutely. Here's a customer who is reporting a possible service issue. We need to take a look at it as quickly as possible, understand the problem, help the customer out. Here's another example. A customer is reporting a feature request, and it's incredibly important for us to listen to our customers. So we would like to know about this feature request soon after it comes in and route it to the right team within AWS. Here's a third example. This is something we hate to see. It's a customer who is unhappy. They're outright angry here. We need to make sure to understand the problems they're experiencing and make things right for them. And finally, here's a customer that is asking a fairly specific, detailed question. And here again, we want to route this question to somebody who is well qualified to answer it and help this customer out. These are 4 examples of important things for us at AWS to listen for in social media streams, and of course your businesses may be different. There is an obvious question here. Do we really need machine learning for this? Isn't it just a matter of listening to social media streams? And the answer is yes, we do need machine learning because in our experience, most of the social media stream is not customer service actionable. And it's also very high volume. It's hard to keep up with all the messages that come in. So let me show you a few examples. Here is a real tweet, again, addressed at AWS Cloud. It's customer is making a joke. It's a great joke. There's nothing for customer service agent to do here. Here's a tweet that mentions AWS Cloud handle on Twitter, but in fact, it's a promotion tweet for news articles that was written comparing different AWS Cloud regions. There is, again, nothing for customer service agent to do here. A third example is a conversation between 2 customers that mentions AWS Cloud. Nothing for customer service to do except to stay out of the conversation. And finally, here's an example we love to see. It's a happy customer. They're saying thank you to us, and we really appreciate it. But there is nothing for a customer service agent to do with this tweet. And in our experience, upwards of 85% of all messages that mention AWS Cloud are not customer service actionable. And we really want to find the 15% that are and make sure that our customer service agents are looking at them. Before we go on, I want to talk about Amazon Machine Learning for those of you who have not had a chance to take a look at it yet. Amazon Machine Learning is a new service from AWS that is intended for developers, people who are already most connected and familiar with data instrumentation, pipelines, and storage, to be able to use machine learning technology easily and quickly to build predictive applications. It is based on some of the same robust ML technologies that's already used within Amazon's internal systems, generating billions of predictions on a weekly basis for businesses across Amazon. Amazon Machine Learning is built to make it simple and reliable to use the data that you're already storing in the AWS Cloud in products like Amazon Simple Storage, or S3, Amazon Redshift, and Amazon Relational Database Service. And lastly, and very importantly, Amazon Machine Learning is built to eliminate the gap between having models and having these models actually used by smart applications. Production deployment of models with Amazon Machine Learning is only a click away. All models are automatically monitored, and great APIs are available to integrate the predictions produced by these models into your applications. All right, so here's the problem we would like to solve. We want to instantly find new tweets mentioning AWS Cloud Handle, ingest and analyze each one to predict whether a customer service agent should act on it, and if so, send that tweet to the customer service agents. And to do this in real time, robustly, and reliably, it's not easy, but luckily we have services available that we can string together to build our entire application with only a few hundred lines of code. So let's step through that. Finding new tweets mentioning AWS Cloud, of course, we have to go to the authoritative data source here, which is Twitter, and Twitter has several APIs that we can use to retrieve tweets as they appear. To ingest these tweets as they come in, we'll use Amazon Kinesis, a real-time scalable data processing service, to bring, and we'll use it to bring in our tweets into AWS Cloud. Once we have the tweet, we'll use AWS Lambda, which is a managed compute service that runs your code in response to events. Our application is clearly event-driven. We have a tweet coming up as an event, and we want to predict whether it's customer service actionable or not. So we can just write a few lines of code and have Lambda manage the coordination and scaling of our entire application. It's easy to use, it's reliable, and it's fast. Finally, we have Amazon Machine Learning. Amazon Machine Learning will be used to inspect an individual tweet that's coming in and decide whether it's customer service actionable or not. And once we do find tweets that are actionable, we'll use Amazon SNS to distribute this tweet these tweets to customer service agents. SNS can send events or messages to a variety of applications. In our case, we will connect it to an email application. So customer service agents will instantly receive an email when a new actionable tweet is detected. Our process of building smart application has 5 steps, and these 5 steps are fairly standard across many different types of machine learning applications and across the entire machine learning industry. We start by picking the machine learning strategy, by deciding how will we address the problems that we want to solve with machine learning. Then we'll prepare our data. We'll follow up by creating a machine learning model and evaluating it and making sure that its outputs are aligned with business objectives. Finally, we'll write and configure our application code that is responsible for message routing, and we'll try it out. We'll finish up with a demo. So let's start by picking our machine learning strategy. The question we want to answer is, again, looking at an individual tweet and deciding, is this tweet customer service actionable or not? The data we have available to us is text and metadata from past tweets mentioning AWS Cloud, and that is what we'll be looking at to find patterns that connect data and this data and metadata to the thing that we're trying to predict. Is it actionable or not? And the specific machine learning approach that we'll choose to use here is a binary classification model. Binary classification models are used whenever you have a situation where you need to pick one of 2 possible answers. So yes or no, 1 or 0. In our case, of course, is this tweet customer service actionable or is it not actionable? All right, we have our strategy. Let's prepare our data set. And here we can start diving into just a few lines of code. We'll start by collecting past data. We'll use Twitter API to search for tweets from the past containing our company's handle, AWS Cloud in this case. And it's pretty simple. We issue a request and we get paginated results, and we can go back in time and walk through the pages to gather as many results as we need. And there are good news and bad news here. The good news is the data we get from Twitter API is well structured, it's reasonably clean, we don't need to spend a lot of time cleaning it up. The bad news is Twitter will tell us what tweets have occurred in the past, but Twitter will not tell us which of these tweets are customer service actionable or not. They don't know. It's really specific to our business and our application. So what we need to do is we need to annotate the tweets that we'll use to build our machine learning model with this field. It's called label in machine learning vernacular, of whether it is customer service actionable or not. We do this on the data points from the past, and then as new data points come in, our machine learning model will predict this label, so we don't have to. Annotation can be hard work. It's kind of fun to look at a small number of tweets. You can do 100 or even a few hundred, but we need a few thousand. And so wouldn't it be great if there was a way to pay someone to collect these annotations? And in fact, there is that way. Amazon Mechanical Turk is a marketplace for tasks just like this one, tasks that require human intelligence. So let's go ahead and look at what it looks like to use Mechanical Turk to request and collect labels for our tweets. Here we have a screen of what Mechanical Turk console looks like. What we want to do here is create what's called a human interaction task, or HIT. And there are many templates available in Mechanical Turk, but we will create our task from scratch. We start off by describing our task, and these descriptions and keywords that we configure on the screen help Mechanical Turk workers find the task that they're interested in. So we include a title, a description, a few keywords. Next, we configure our HIT properties. We start off by configuring our reward. How much are we willing to pay for each tweet that is labeled by Mechanical Turk worker? Next, we configure a number of assignment per hit. By default, we can leave it as 1, which means that each tweet is looked at by exactly 1 person. It is often a good practice to include an overlap, to have each tweet looked at, as we have in this case, by 3 different people, so that we can have a higher level of assurance that the label is correct by looking at agreement among multiple folks who have processed a tweet. And then we configure a few other metadata properties, like how much time is allowed per hit assignment, and how long are we willing to wait before the task expires. Once we do that, we get to design a template for our Mechanical Turk workers to see. And in our template, we can put instructions, we can put samples, and then we configure the actual task. So what I'm asking in this template here is I'm asking the Mechanical Turk worker to make a choice, to look at a tweet and say, is this tweet from a customer making a request? Are they asking a question? Are they reporting a problem? Are they angry or unhappy? Or is it none of the above? You'll recall that we've said earlier that we'll build a binary classification model, one that just describes is this tweet actionable or not. And in this little taxonomy that I made up, the first 4 choices correspond to yes, this tweet is customer service actionable. And the 5th one corresponds to no, it's not. Now, we don't have to collect this granular information. We could just ask the direct question of, is this tweet actionable or not? But I have a hunch that maybe further down the road, we'll want to build a model that's a little more granular, that answers the question of, what is the root cause of this customer contacting us? And so it's a good practice to collect this kind of data, even if you're not going to use it immediately, to collect more granular data than you need for the immediate task. All right, once we've created our template, it's now a simple matter of uploading a CSV file containing all the metadata of our tweets. The metadata gets populated into the template we've created, and we can publish a batch, and off we go. Now the task will appear in Mechanical Turk Marketplace, and provided that we've specified sufficient reward, it will be completed. Once the results come back to us, we can reduce them again to this 0 or 1 field, which I call training label here. And let's just walk through a few examples here. So here is a tweet, and our label is 0 because I'm saying here that this tweet is not customer service actionable. Here's another example. Clearly a customer who is requesting help. Yes, it is customer service actionable. Another example of a customer looking for a tutorial of how to build an application in AWS Cloud. Of course, customer service actionable. Another example of somebody reaching out to AWS Cloud directly to help with an event. Yes, it's actionable. And finally, an example where TechMeme is calling out all their sponsors on Twitter, of which AWS Cloud is one, not customer service actionable. All right, now we have our data set. Let's move on towards building our machine learning model. The process of building our model is pretty simple, and you'll find a very similar process no matter which machine learning tools you use. First, we create our data sources. Data sources are objects in Amazon Machine Learning that point the service to the data that will be used to create machine learning models. And they also contain some useful metadata. For example, what are the different names and what are the different variables in this data? What are their types? What is the format of the data set? And we'll create 2 data sources. We'll create one data source that will be used to actually train our machine learning model. We'll create a second data source that will be used to evaluate our model. And the 2 data sources are disjoint, so our evaluation is going to be very fair because we will not use any of the tweets that were used to train the model to also evaluate it, which prevents the model from simply remembering the correct answers. After we create our data sources, we'll dive into the console and we'll actually take a look at our data to make sure that it looks as we expect it to. Once our data sources are complete, the next step is to create a machine learning model, and that's just one API to build a model with smart defaults, or we can configure custom settings. Next, we'll evaluate our machine learning model, and that's again one API to compute model's quality. And finally, and this step is absolutely crucial, we will use our Amazon Machine Learning console to align the outputs of the model with the business goals, to make sure that the model is maximally correspondent to what we want to achieve with our application. And we'll see what that looks like. Throughout these examples, I'll be showing you API calls You can do all of these steps through the console as well. And in fact, it is a good practice to start with creating your data sources, creating your machine learning models, and evaluating your machine learning model all through the console. But I'm using the API code path here to show you how to not only create these models, but also how you can automate this process. So let's start with data sources. The first step to creating our data source is to create our data schema. Data schema is just a small JSON document containing metadata about our data set. What format is it in? CSV in our case. What are the names and types of different attributes in our file and what orders they're in? And the names of special attributes, like our target attribute, this thing we try to predict. So this is a very simple JSON document, and we save it into a string. Once we have that string, now it's just one API call to create our training data source. We start by making a data spec structure, which has a pointer to our data location in S3, and it has our data schema location, our data schema, which we just saw in previous slide. And then we instruct Amazon Machine Learning to go and retrieve the data stored in the S3 location we specified above, and only take the first 70% of the data and use it for training. And now all we have is to call the create data source from S3 API, and you can imagine there is an equivalent API to create a data source from Redshift and create data source from RDS. We specify the name of the data source that we want our data source to have. We specify its ID, and we specify a flag called compute statistics, which triggers Amazon Machine Learning to go and compute descriptive statistics on the data, and we'll take a look at the outputs of that in just a little bit. So here's our API call again to create the training data source. The creation of the evaluation data source looks almost identical. The only difference is that we instruct Amazon Machine Learning to take the last 30% of the data instead of the first 70%. And of course, we give a different ID and name to the new data source we're creating. Having done so, let's go ahead and visually inspect training data. Here is a screen of what it looks like in Amazon Machine Learning console to look at the data source. We have a few alerts that run automatically to tell you about potential conditions in your data. If you take a look at the bottom of the screen, you have a target visualization. Let's click on that to zoom in. So here we look at our target variable, which again is 0 if a tweet is customer service, the tweet is not customer service actionable, and 1 if it is actionable. And in this case here, as we expected, far fewer tweets are customer service actionable than non-actionable. But we don't have to look at just the target. We can, of course, look at distribution of any variable in our input data set. We can zoom in and take a look at distributions. So what I'm looking at here are the screen names of users who left tweets in our training data set. And just as I expected, it's a very long tail distribution. Most of Twitter users make a small number of tweets, certainly those that are aimed at AWS Cloud Handle. We can see at the leftmost side of this histogram that the most frequent Twitter user that mentions AWS Cloud in our data set is Stack Careers, which is a job announcement bot. And there are a few other automated Twitter bots in this top 10 list. But the bulk of the tweets are in the other tab, which is all the way to the right and in blue. And we can actually zoom all the way in and take a look at individual tweets that have been made by different handles by just clicking on any one of these bars in our histogram. So here we look at Hans B001 screen name, and we see the description of that user, and we can switch over and take a look at the specific tweets we've made. The purpose of doing so is to visually inspect your data, and when something looks unusual, you can use the tool, the Amazon Machine Learning Service Console, to dive right in without going back and pulling up your data and finding the point of interest. And this is incredibly powerful. Machine learning, like any other data analysis, adheres to the garbage in, garbage out principle. We need to make sure that our data is well formed and is correct as it goes in. And there is a great way to do this just by looking just by doing a few quick sanity checks. All right, we took a look at our data sources. We made sure that the data looks as we want it to. Now we have a simple API call to create a machine learning model. It's literally called create ML model. We start off by passing in machine learning model ID and names that we want this model to have. We pass in our model type, binary classification, and we pass in the training data source IDs that we created earlier. And that's all we have to tell Amazon Machine Learning to enable it to go find the data, to build the right kind of a model, and to configure this model for best performance. If no other options are specified, Amazon Machine Learning will apply smart defaults to build a high-quality model with the data you've created without any other instructions. And these defaults are actually specific to the data that you've provided. These are not the same defaults to everyone. In the previous step, when we created our data source and we chose to compute data statistics, we've enabled Amazon Machine Learning to use these data statistics to inspect the data and to suggest data transformations that will optimize the model quality. And these data transformations will be applied automatically if you don't provide your own set of transformations and options. Having created our machine learning model, we can go ahead and evaluate it. Evaluation is also one API call away. And what happens in evaluation process is Amazon Machine Learning goes and computes a quality metric. And machine learning quality metrics are pretty tricky. There are well-accepted metrics for different kinds of models, and Amazon Machine Learning has a different metric built in for the 3 different kinds of tasks that we support, whether it's binary classification, multi-class classification, or regression. So what we did here is we simply request an evaluation, and Amazon Machine Learning will know what kind of metric to compute based on the model type. And let's take a look at what that looks like. Once our metric is computed, we can retrieve it programmatically, or we can hop into the console and take a look. We can see here that the metric we computed is called AUC, or area under curve, and its value is 0.85 for the model we created. Metrics are relative to the difficulty of the problem we're trying to solve. For most kinds of machine learning applications, an AUC metric of 0.85 is pretty good, but of course it depends on the application, it depends on how much data we have. Having understood the summary quality of the machine learning model, next thing we want to do is configure this model to align, configure the model's outputs to align with our business goals. I want you to consider for a second what kind of mistakes can this machine learning model make. Given that we're predicting a binary attribute, is this tweet actionable or not? We can have false positives, which is tweets that are not actionable that we predict are actually actionable. And we can have false negatives, and these are tweets that are actionable, but the machine learning model said that they're not actionable. And of course, in general, we want to have as few mistakes as possible. But given that a mistake is going to happen, we get to have a choice of what kind of mistakes are more costly for our business, and we get to minimize those. So I'll claim here that false negatives are a lot more costly kinds of mistakes for this specific application. If we have a false positive, it means that we send a non-actionable tweet to a customer service agent, and provided that the number of false positives is small enough, they can just ignore it and move on. But if we have a false negative, what we have is a customer who is reaching out to us because they need help or assistance, and we ignore that. That is really expensive. That is not the right thing to do. We want to minimize the number of false negatives. So if you take a look at this plot in front of you, and you take a look at the numbers in red at the bottom, we can see that with our current model, we have 7.6% rate of false negatives and 4.7% rate of false positives. The way this rate is computed is by taking the output of the model, and the model does not tell us whether the tweet is actionable or not directly. What it tells us is the probability of the tweet being actionable. And that probability is a number ranging between 0 and 1. So we take that number and we evaluate it against a threshold. And by default, the threshold is 0.5. You can see it in the text box in the upper right corner of our screen here, which is to say, if the model is at least 50% sure that this tweet is actionable, go ahead and mark it as actionable. But what I can do here is I can grab the slider as it controls the balance, as it controls the threshold, and indirectly then controls the balance between false positives and false negatives. And I'm going to drag it all the way to the left. Let me play this again for you. Here's our slider, and I'll drag it all the way to the left. And what I've done here is I've reduced the number of false negatives from 7.6 to 5.1%. My number of false positives went up as a result, but because I know that false negatives are so much more dangerous to my business than false positives, it's a trade-off I'm willing to accept in this case. So at this point, we found our desired threshold, which is 0.07, or in other words, if the model is at least 7% sure that the tweet is customer service actionable, go ahead and mark it as actionable. This is a better safe than sorry kind of strategy. And we can save this threshold, and from now on, the predictions that we get back from Amazon Machine Learning, they will always include the raw score, but they will also include a label 0 or 1, and the label will be based on comparing the score against this threshold set at 0.07. All right, so we have our model. Now it's time to write some code. Let's build our application. Here again is our data flow. Events start at Twitter API. We have tweets that mention AWS Cloud. They flow in through Amazon Kinesis. Then AWS Lambda functions run in response to these events and coordinate application flow. And what they do is make a call to Amazon Machine Learning to get a prediction of whether a tweet is actionable or not. And if the tweet is not actionable, the flow ends right there. If the tweet is actionable, then it is sent to Amazon SNS, which then distributes it to the final destination. So let's go ahead and start connecting the dots here. We'll start with Amazon Machine Learning. We already have a machine learning model created. Its threshold is already configured. The only thing we need to do now is to enable this model for real-time predictions, to deploy it into this production fleet. And that is a single API call away. We create a real-time endpoint, and the API is called create real-time endpoint. We provide our model ID, and now our model is accessible for real-time predictions. It will have a URI that can be used to send JSON formatted requests to, and we can grab this URI by describing the model by calling the getMLModel method when we need to. So great, our model is up and ready. It can serve requests as they come in. Next thing we'll do is we'll create a Kinesis stream. And Kinesis is, of course, responsible for piping the data from Twitter and into our interactive flow. It's a simple API. We just create a stream. We provide a stream name. And we provide a measure of how much capacity is needed to be provisioned. Kinesis counts capacity in units of shards. Each shard can support up to 1,000 record writes per second, and in total of up to 1 megabyte written per second, which is plenty for our application. For more high-volume application, you would set the shard count higher than 1. With Kinesis having been done, the next thing we do is build our Lambda function. And there are 3 things to be built here. We need to write the codes that will process and route the tweets to the right place. We'll configure the Lambda execution policy to very tightly scope down what this function is allowed to do. And then finally, we'll add the Kinesis stream as the data source for our Lambda function to enable the flow from among all the components. So let's look at the code. I have here just a snippet of a few global variables being declared and 4 functions that we'll create. And these are 4 very simple functions. I won't walk you through the actual code for these functions. I'll only show you the signatures. But again, as a reminder, you can download all this code from our GitHub repository. And the code is pretty simple. We have a function called process records, which simply takes the Kinesis payload and base64 decodes it. and then parses out the JSON format. We have a function called callPredict, which actually calls out Amazon's machine learning real-time prediction API to obtain prediction. We have a function called updateSNS that publishes customer service actionable tweets, those that have been predicted as positive, to the SNS topic. And then finally, we have a function called check real-time endpoint, and this function connects to Amazon machine learning and discovers what is the URI for our real-time machine learning endpoint that is used by the callPredict function here. This is all the code we need. There is about 150 lines of code total, and it's all pretty simple. Moving on, we will configure our execution policy. And this is really important because we want our Lambda function to only be able to do the things we want it to do. We don't want it to be a completely unscoped code execution environment. There are just 4 parts to this execution policy, and I'll quickly walk you through them. We start off by creating a statement that allows our Lambda function to log its requests in Amazon CloudWatch. Next, we have a block that allows our Lambda function to call just one API of SNS, and that is published. So it can write to an SNS topic, and it's a topic that we specify, not any arbitrary topic. And that's all this function can do with SNS. Next, we have a little policy statement that allows our function to call Amazon Machine Learning's real-time prediction API. And so we allow access to just the predict API and also to the getML model API, which retrieves model metadata containing the URI of this API endpoint. And again, this is scoped down to specific account, specific region, specific model ID. So it's very tightly scoped to just our application. And finally, we have a block that allows our Lambda function to read data from the Kinesis streams that we configure. And there are a few APIs that we give access to, but they're all read-only APIs that enable stream access. So now we have our policy. It's time to finally connect all the dots here. And we do that by calling a Lambda API called addEventSource. We provide our event source, which is a Kinesis stream. We provide the function names that we want to run in response to this event, which is process tweets. And finally, we attach the execution role, which we just configured. And that's it. Our application at this point is completely configured. It is deployed. It is ready to receive prediction traffic as it comes in. So now let's try it out. I'm going to show you a tweet. Here's a pretty simple tweet that I grabbed from Twitter. And we have a customer advertising as Amazon S3 wrapper. So this is a view as you would see it if you logged into Twitter yourself. Now here is the same tweet as a JSON blob. This is a view you would get if you called Twitter API to retrieve it. We have the tweet text, we have the username, we have the number of favorites for this tweet, and so on and so forth. So to get a sample prediction, we can use the command line interface of Amazon Machine Learning to just see what prediction looks like. And it's pretty simple. We say AWS Machine Learning Predict. We provide prediction endpoint, which we can obtain from our model. We provide machine learning model ID. And finally, we provide the record, which is the JSON blob that we just saw in our previous slide. And immediately, a response comes back. Most of the responses will come back in well under 100 milliseconds. And here's what response looks like. It has a section called prediction. We get our predicted score, which is 0.0123 and so on and so forth, and predicted label, which is 0. You may recall a few minutes ago we configured our model to say, if you're at least 7% sure this tweet is customer service actionable, go ahead and mark it as actionable. But in this case, the model is only about 1.2% sure the tweet is actionable, and therefore we mark it as predicted label as 0, which our application can interpret as not actionable. So here is one sample. And let's take a look at our flow again. We have data coming in from Twitter, hitting Kinesis, then Lambda. Lambda coordinates a prediction flow, and then actionable tweets go to SNS. So why don't we take a look at an end-to-end application demo? I'm going to switch over to my application screen. And what I'm looking at is a Twitter, my tweet screen. One moment. Apologies.
Alex, can you switch back over to Adobe and initiate the screen share?
Let me set that up really quickly. So here we are looking at a Twitter screen, and I'm just going to send off a couple of tweets. I'm going to start off by sending a tweet that I grabbed from our data set. We saw it a little earlier. Here is somebody who is asking for a tutorial on using S3 with Rail and Heroku. Going to go ahead and tweet that. And I'm going to share another tweet, and we also saw this earlier in our presentation. Check out TechMeme sponsors on Twitter, and AWS Cloud is mentioned here, so I'm going to go ahead and tweet. So what I expect to happen now is these tweets to go in through our pipeline, and I'm going to start off by going into Lambda. Here is our function classify tweet. I can click on that, and let's go to monitoring. I can look at the logs that have been output by CloudWatch. And I see an event here, so let's go ahead and click it. Here is our tweet that we've executed. Anyone know a slow tutorial? And you can see that next what happened is we called the predict function. The predict call succeeded, and we called Amazon SNS to publish. And I will hop back to our console. Next, I will look at my SNS topic. I'll quickly show you that I have an SNS topic configured to deliver tweets that are sent to this topic to my email address. And finally, I can log into Workmail, and our tweet just showed up. Here it is with its timestamp of 9:42 a.m. Here is an email that would have been sent to our customer service agents. It says, here is an actionable tweet. Please click here to respond to it. So we can click on it, and there is that tweet that we just sent off. So in a matter of less than a second, a tweet was published, it was responded to, we got a prediction, we ensured the prediction was positive, and then as customer service agents got this email. The second tweet that we sent, the ones that was not customer service actionable, it was run through the prediction, it was confirmed as being not actionable, and so no email came in. I'll switch back to my work docs here again, and you can see there's still only one email. So now I'll switch back to my presentation, and we took a look at our demo. So you might ask at this point, isn't this just still a whole lot of trouble just to listen to one social media channel? Here we went off and we built a data set, we labeled it, we created our machine learning model, evaluated it, created some Lambda functions. The key thing to realize there is what we've built is a highly repeatable flow to adapt to all kinds of different channels, not just Twitter. This could be, we could use the exact same flow to read data, for example, from your Facebook, from your company's Facebook account, maybe emails, maybe reviews, maybe other things that your customers use to contact you. For each one of these, we would build a different machine learning model. People use Facebook in very different ways as they use Twitter, and people write emails using typically more than 140 characters. And so these are very different. But other than plugging in an appropriate model for each input type, the general flow remains exactly the same. And so this is now a very powerful application pattern to build social media listening or listening to your customers through even non-social media channels and have a repeatable, robust infrastructure for doing so, all in AWS Cloud. So where do we go from here? I would encourage you, of course, to try Amazon Machine Learning Service if you haven't already. You can find it at aws.amazon.com/machine-learning. Please go ahead and download the social media listening application code. Here's the bit.ly link to do so. And as a reminder, again, you will get these slides after the presentation, so you'll have the link available to you. And what you'll find in the GitHub repository is all the sample code to build our application. A sample data set that's been trained to build, that's been trained on data that has been sent against AWS Cloud Handle. And we even included a little program to poll Twitter and retrieve the tweets that can be then fed into the Kinesis stream. So it's everything you need to try it out on your own. And if you have questions, please feel free to get in touch. My email address is Ingerman, that's spelled INGERMAN @amazon.com. We would love to hear from you. And at this point, I'll turn it over to Bowen again.
Thank you, Alex, for the great presentation, and Nicole, Victoria, and Charles for answering the questions throughout today's presentation. We will now start the Q&A session, but apologize in advance that we might not be able to get to everyone's question. An audience, if right now you can take a few minutes to fill out 3 poll questions, and that's listed on the left side of your screen. We have about 12 minutes, so please feel free to continue submitting questions at this time. So Alex, whenever you're ready.
Certainly. Okay, we have a few questions here, and I'll try to run through as many as I can. So first question is, what is the Twitter API code written in? The language I used throughout this presentation is Python, but everything we have shown today translates to just about every popular language out there. So using AWS SDK, you can interact with all AWS services in a variety of languages. You can interact with Amazon Machine Learning specifically in languages including Python, Java, JavaScript, PHP, Ruby, and perhaps 1 or 2 others. And to talk to Twitter APIs, it is also possible to do so in a variety of languages. Okay, then we have a question of, are the S3 and machine learning APIs standard REST APIs that could be coded in a language outside of ones listed in your SDK? The answer is yes. You can write code to connect to the APIs directly. If you take a look at the AWS user guide, you will find example code for how to sign your own requests, and you can send the payload directly. In the Amazon Machine Learning API reference, you will see sample payloads for both input and output. So you can use a client library of your choice, just like I mentioned in the previous question, or you can write your own requests, whatever you prefer. All right. Next question is, approximately how many tweets were used to train, and what was the cost of Mechanical Turk tasks? I don't have the exact cost in front of me. As I recall, we trained on about 9,000 or 10,000 tweets. We've specified an overlap of 3 tweets, three workers looking at each tweet. And I believe we left our reward at the default 5 cents per. So I won't pretend to do the mental math because I know I'll get it wrong, but I think that was about the total cost of the process. And then a related question is, did we really set this task to Mechanical Turk? How many answers did we get? Yes, we really did send it to Mechanical Turk. In the GitHub repository, you can find the template that we used to send the task, and you can find the script that we used to collect the raw data from Twitter and then convert it to a format that we can upload to Mechanical Turk. So if you would like to repeat this experiment with your own data, all of that is available to you. It will really make things go really fast. Okay, then we have a question of how long did the machine learning model building process, show an example, take in real time? I don't have an exact answer, but I would expect that the model building shown here took a minute or so. It's a fairly small data set, and we would run through it very quickly. Okay, we have a question of how often is the Lambda function involved and what is the event that caused this invocation. The Lambda function was involved whenever a tweet appeared, and the event was a new tweet being pushed into the Kinesis pipe. So if you recall, we had a slide where we configured our Lambda function to give it the event source. The event source was the name of our Kinesis stream. So when a tweet appeared, we have a little daemon and a code for that is available on our GitHub as well that retrieves it and pushes it into Kinesis pipe, and that triggers an event that is then responded to by Lambda. And our little code snippet that obtains events is in turn listening to Twitter's own real-time search API. So at the end of the day, the flow is a tweet is published, Twitter has a real-time API to inform a listener that this tweet is available. Our listener pushes the tweet to Kinesis, Kinesis involves Lambda, and off we go. Okay, let's see. We have a question of, is Amazon ML designed keeping in mind first-time machine learning users or regular machine learning practitioners and experts? The answer here is we built Amazon Machine Learning to enable developers who do not necessarily have experience with machine learning to use the service. What we find is machine learning practitioners often do use the service as well. We offer some really nice things to this audience in terms of being able to deploy models at scale, to have reliable APIs to build and evaluate these models, and generally to scale out their bandwidths. So we find that our customers come from both machine learning novices and experts and everywhere in between. Okay. There is a question of how does machine learning evaluate to label new tweets 0 or 1? Did the speaker code for that? The machine learning model evaluates tweets as they come in and labels them as 0 or 1 based on the training data we provided. So if you recall, we collected our training data from Twitter, and then we ran it through Mechanical Turk, and then we labeled the results that we got back from Mechanical Turk as 0 or 1. So now we have a model that knows that given a tweet as input, its task is to produce an output as either 0, this tweet was not actionable, or 1, that it is actionable. And this information has been carried all the way through the Amazon machine learning stack simply because we created a data source which had a label field that was set to binary type, and then we created a machine learning model and we instructed Amazon machine learning to make it a binary classification model. Okay. Next question is logistic regression the default binary classification model? The answer is yes, it is, and in our developer guide, you will find a more detailed description of which algorithms are used by Amazon Machine Learning in response to different machine learning tasks, whether it's binary classification, multi-class classification, or regression. Okay. We have a question of, is the default setting of machine learning to parse tweets and evaluate it by words? This goes back to the default, to the smart defaults that have been applied as a part of training the machine learning model. One of these defaults is for Amazon machine learning to take all inputs that have been declared as text inputs, and by default it will break them up into individual words, and then each of these words is an individual signal that helps our model learn. As a user of Amazon Machine Learning, you have quite a bit of control over that. You can specify breaking not into individual words, for example, but into groups of words. You can apply processing, for example, lowercasing, because we may not care the case in which a word was written. All of that is available. What we find is simply by breaking the incoming data on word boundaries, we get incredible lift in the performance of our model just by taking a look at this text data. And Amazon Machine Learning enables us to do this at scale without throwing any data out, without selecting out just a few words in the vocabulary. It uses all the text that comes in. And that's a part of why this Twitter model works pretty well, straight out of the gate with no additional processing. Okay. Question As a machine learning practitioner, how would I go about learning basic development skills to learn to create the pipeline design on AWS? I would recommend taking a look at the sample that has been published, demonstrating the flow that we've gone through in this session. There is quite a bit of information along with the sample in the README file on Twitter, on GitHub, that will explain the process in much more detail and give you additional information. And you'll be in a good place to get started with that. And of course, we have other help topics available. We have a developer guide, an API reference, and you will be able to build a pipeline much like the ones that we've looked at today pretty easily by just following this guidance. Next question is, can Amazon Machine Learning learn from online streaming events? The answer is not out of the box. We do not have a setting in Amazon Machine Learning today to learn from events as they come in. Something that can be done that is pretty effective is you can use a Kinesis product called Kinesis Firehose to take new data as it comes in and put it into either S3 or Redshift. And Redshift will probably be a better choice for this application. So now you have a pipeline to capture data and put it into permanent storage. And then you can set up a scheduler to create new machine learning models based on whatever is in that Redshift table, and do that at fast iteration, for example, every hour. So it's not online learning in the sense that each new data point does not impact the model immediately, but it accomplishes much a similar goal. It ensures that the model stays reasonably up to date, and by altering the frequency at which you create models, you can control what degree of delay is acceptable to you. There are a couple of questions asking whether your own machine learning models can be incorporated in this framework, and the answer is no. Amazon Machine Learning is built to run algorithms that we provide within the system, and it is that allows us to run them at high speed and reliably. There is a question of using data that resides in DynamoDB and is updated on a live basis. And the question is, do you have to move it to Redshift to use Amazon ML? Amazon ML today cannot connect to Redshift data source, so the recommended practice would be to move it to another data store. Redshift would be a fine choice. S3 is also an option. You may even choose to do something like use DynamoDB's built-in functionality to back up the data to S3. Now that backup will not be in a CSV format that Amazon Machine Learning can read, but you can connect a small script to that to convert from DynamoDB's backup format to a CSV format and go from there. You might find that Redshift might be less trouble to accomplish the same thing. There's a question of whether this approach can be applied to different languages. All our tweets were in English, but can this approach work in Spanish, German, or Chinese? The answer is that for languages which separate words by spaces, such as Spanish or German, absolutely. There is actually nothing in what Amazon Machine Learning does that is specific to English. It takes input and it tokenizes based on spaces and then learns patterns from it. So whether a word is in English or Spanish or German makes no difference. This is a little more complicated when it comes to using a language like Chinese, which does not by default have word breaking. In this case, you would want to process the inputs before they arrive to Amazon Machine Learning to separate the sentences into individual words. Once you do so, yes, absolutely, Amazon Machine Learning will learn from words in Chinese just as well as from words in English. Okay. Let's see. I'm just scanning quickly through the list of our questions. There is a question of, let's see. There is a question of whether Amazon machine learning supports R code. And the answer is no. Amazon machine learning runs with the models and the environments that we provide, and we're not able to run R code at this time. There is another question of whether Amazon machine learning is geared towards assessing images, since the example we gave was a text example. And the answer is not at this time. This is something we're evaluating, but we don't have specific plans yet on what or when we will do with images. There's another question of, are there guidelines about the minimum size of a training set that is needed to get good results for various types of projects? And this is a question to which it's very difficult to give a prescriptive answer to. Unfortunately, it really depends. It really depends on the difficulty of the problem. It really depends on how much signal is in your data. What we recommend is trying with the data sets available to you, and if the results are not meeting your expectations, you may consider adding more data.
Great. I'd like to extend a special thank you to our presenter, Alex, for his time and a great presentation, and Nicole, Victoria, and Charles for answering your audience questions. And thank you also to our audience for taking the time to join us today. Enjoy the rest of the day.